The quantum nature of gravity. Look up at the night sky. What you see, the pinpricks of light, the silent, graceful arc of the moon, the vast, empty darkness between them. It's all governed by a force so familiar, yet so profoundly mysterious, that it has humbled the greatest minds for centuries. Gravity. It's the force that grounds us, that holds the cosmos together. We all know its story, the tale of the falling apple and the genius of Isaac Newton. He gave us the what? A magnificent description of how objects attract each other. Then, a century ago, a man named Albert Einstein gave us a vision so radical it shattered that clockwork universe. He told us that gravity isn't a force, not in the way we think. It is the curvature of space-time itself. Mass and energy tell space-time how to bend, and space-time tells matter how to move. It's a cosmic dance, a geometric symphony. This picture, general relativity, is breathtakingly beautiful. It predicted black holes, the bending of light, the expansion of the universe itself. It works on the grand stage, the cosmic scale. But when we peer into the heart of reality, into the impossibly small world of the quantum, this elegant picture shatters into a million pieces. And that, right there, is the greatest unsolved mystery in all of physics, the quantum nature of gravity. Why is this such a profound problem? Imagine the universe is built from two separate languages. One language, the language of general relativity, speaks in smooth, continuous curves. It's the language of landscapes, of rolling hills and deep valleys. It's a classical language. The other language, the language of the quantum, is the language of the ultra-microscopic. It is a language of wild probability, of flickering existence, of particles that are also waves, of fields that jitter and dance with a fundamental, unstoppable energy. This is the quantum vacuum, not true emptiness, but a seething, bubbling foam of potential. In this realm, nothing is certain, and reality itself is a shimmering cloud of possibility. For nearly 100 years, these two languages have been unable to speak to one another. Our theories of the quantum world, which describe the other three forces of nature with incredible precision, simply break down when we try to apply them to the curvature of space-time. It's as if you have the most perfect, detailed map of a single nation, but when you try to place it on a globe, the paper crinkles, tears, and turns to dust. The central conflict is this: what happens to space and time themselves when we look at them under a quantum microscope? Einstein showed us that space-time is a dynamic, flexible fabric. But if everything in the universe is ultimately quantum, then this fabric cannot be smooth. It must be woven from something. It must have a smallest possible unit, a fundamental pixel of reality. Think of your computer screen. From a distance, the image is smooth, continuous. But zoom in, and you see the pixels, the discrete bits of information that make up the whole. What if reality is like that? What if space-time itself is pixelated? This isn't just a wild guess. When we try to push our equations into the heart of a black hole, or rewind the clock to the very first moment of the Big Bang, our maths scream in protest. They produce infinities, nonsensical answers that point to a deeper truth. We are missing the fundamental code. This is where the magic begins. This is where physics meets philosophy, and the line between science and mysticism starts to blur. Let's talk about black holes. These are the ultimate gravity labs. According to relativity, a black hole's core, its singularity, is a point of infinite density where space-time curvature becomes infinite. The laws of physics, as we know them, simply cease to exist. But nature abhors an infinity. It's a sign that our theory is incomplete. Then, in the 1970s, a physicist named Jacob Bekenstein, followed by the legendary Stephen Hawking, made a discovery that shook the foundations of science. They found that black holes are not entirely black. They have a temperature. They glow. They evaporate, slowly releasing particles back into the universe. This is Hawking radiation. And here's the mystical part. This glow is inextricably linked to information. The surface area of a black hole's event horizon, the point of no return, seems to be a measure of its information content. It's as if all the information about every star, every planet, every atom that ever fell into the black hole is not lost in the singularity, but is somehow encoded on its two-dimensional surface. Let that sink in. A three-dimensional volume, an entire universe of stuff, could have all its information painted on its two-dimensional boundary. This is the holographic principle. It's the radical suggestion that our perception of a three-dimensional universe might be a projection, a hologram, from a two-dimensional surface at the very edge of everything we can know. This isn't science fiction. It's a serious, leading candidate for a theory of quantum gravity. It suggests that reality, at its most fundamental level, is not what it seems. We are living in a cosmic illusion, a magnificent projection. The solidity of the chair you're sitting on, the feel of the air on your skin, the vast, three-dimensional expanse of the galaxy, all of it might be emerging from a vast, complex network of quantum information stored on a distant, two-dimensional surface. It's as if the universe is a movie, and we are the characters inside it, believing the world to be real, while all the information needed to create our reality is stored on the flat, two-dimensional film reel at the edge of creation. This leads us to other mind-bending ideas, like string theory. Without getting into the complex mathematics, imagine that the fundamental particles of nature, electrons, quarks, photons, are not tiny, zero-dimensional points. Instead, picture them as unimaginably small, vibrating loops of energy, strings. What distinguishes an electron from a photon, in this view, is simply the note it plays, its resonant frequency of vibration. And the force of gravity? That would be carried by a particular string vibrating in a specific harmonious pattern. In this symphony of strings, gravity is just another melody in the quantum orchestra. And this theory naturally requires more dimensions than the three of space and one of time that we experience, curled up so tiny that we can never perceive them. Then there's loop quantum gravity, which imagines space-time not as a smooth fabric, but as a woven tapestry of tiny, finite loops, a spin network. In this picture, space is not continuous. It is quantized. There's a smallest possible unit of space, a quantum of volume. And time? Time may also be quantized, ticking in discrete, fundamental steps, like the frames of a cosmic film. What does this mean for our everyday reality? It means that if you could zoom in far enough past atoms, past quarks, you would not find a smooth, empty void. You would find the very weave of space-time, a vibrant, dynamic, and discrete structure, buzzing with energy and information. So, what are the mystical, the magical implications of all this? First, the nature of time. In our quantum gravity theories, time as we know it might not be fundamental. It could be an emergent property, a story we tell ourselves as the quantum states of the universe evolve. The flow of time, this relentless forward march we all feel, might be a grand illusion, a side effect of a deeper, timeless reality. Second, the universe as a whole. If space-time is quantum, then the Big Bang was not an explosion in space and time, but an explosion of space and time. It was the moment when the quantum tapestry of the cosmos first began to weave itself. Perhaps our universe is just one bubble in a vast, eternal quantum foam a multiverse of cosmic froth, where other universes with different laws are constantly budding into existence. This isn't just about finding a new particle. This is about rewriting the very definition of reality. Unifying gravity with the quantum world is the final step in our quest for a theory of everything. It's the search for the single, elegant, primal principle from which all of physics, all of existence, flows. It is the quest to read the source code of the universe. And we are on the verge. Our experiments are no longer just particle colliders. We are listening for the faint echoes of the Big Bang in the cosmic microwave background. We are using telescopes like the James Webb to peer back to the dawn of the first galaxies. And most thrillingly, we are now living in the age of gravitational wave astronomy. We are no longer just seeing the cosmos, we are feeling it. We have instruments that can detect the ripples in spacetime itself, caused by colossal events like the merging of black holes. Each time we detect one of these ripples, we are listening to the direct voice of gravity. And in that voice, we may one day hear the subtle whispers of its quantum nature. This journey is the greatest adventure of the human mind. It connects the vast, silent cosmos with the frantic, probabilistic quantum world. It suggests a universe that is interconnected in ways we are only beginning to glimpse. A universe that is, at its heart, informational. A cosmic computation of breathtaking complexity. We are not separate from this cosmos. The atoms in our bodies were forged in the hearts of long-dead stars. And the force that holds those atoms together, the force that guides the stars in their courses, is the very same force we are trying to understand. To know gravity is, in a very real sense, to know ourselves and our true place in this magnificent, holographic, and deeply quantum reality. The mystery is deep. The answers will be magical. Thank you so much for joining me on this journey into the heart of reality. If this conversation sparked a sense of wonder in you, if you felt that thrill of the unknown, then please do help this channel grow. Like this video, subscribe to the channel, and ring that bell so you don't miss our next exploration into the mysteries of the cosmos. And I would love to hear your thoughts. What do you think the quantum nature of reality is? Is our world a hologram? A symphony of strings? Leave your ideas, your questions, your own sense of wonder in the comments below. The conversation is my favorite part. If you want to go even deeper, to explore the edges of modern physics and the idea of a holographic multiverse, I've written a book that delves into all of this in much more detail. It's called Holographic Multiverse. We'll explore not just quantum gravity, but parallel worlds, the nature of consciousness, and what it all means for our understanding of existence. If you're interested, the link to check out my book is in the video description below. Until next time, keep looking up and keep looking within. The greatest secrets are yet to be revealed.